Welcome to Chemistry in the AM. I'm not Joel Shindaka, I'm an imposter today. We're going to get ready for a vinegar lab. There's some things we need to know before we start the lab. Some of them will be on paper, and some of them I'll show and demonstrate how the titration works with your reds. So, skills we're going to need. We're going to do this with vinegar, and actually what we're going to figure out, and I'll flip ahead here, but you don't have to. Our purpose eventually will be to find the concentration of acetic acid in 5% vinegar. On the bottle of vinegar that we have, I'll just get by vinegar, it doesn't say how many moles per liter it is. Vinegar is really acetic acid, but vinegar is common, right? So it doesn't say like 1.38 moles per liter. It says 5% on here, and it just says 5%. Now, significant digits. When it says 5%, is that 4.5% to 5.4%? Like, you know what I mean? Is it because it's just one digit, right? How accurate is this 5%? First, from a consumer point of view, or from a science point of view, it's like I said, anywhere between 4.5 to 5.4, right? You can assume it rounds to 5. And then, what does that 5% mean? Do we actually get the moles per liter? But first, we have to understand what does that 5% mean as far as what we've measured in chemistry, moles per liter. So these are kind of where we're going with this, okay? Now, we need calculation tools, and we need to know how to use the actual lab apparatus of your rec, and it's pretty easy. So in order to understand this, and I'm going to more or less give you guys the lab and say, figure it out. So first, I'm going to figure it out with something that's similar. So skills you're going to need. Write the equation for HCl combining with NaOH, sodium hydroxide. So acid HCl, base, NaOH. You guys know this. I'm giving you a moment to write that equation. I'll pause. All right. So we have HCl. That'll be H plus sodium hydroxide, acid plus base. It's salt and water. What is the salt? What is the other compound? You know what water is. I'm going to put it as H. You can put it as H. Okay. Acid plus base, salt, and water. What's the salt? And it is what you just normally call salt. Oh. Okay. And we remember this because what we called last year, you called this double replacement reaction, right? Right? Essentially, that's what happens. NaCl and H, Na and H switch places, and they're both positive ones, so the balance doesn't screw up either. Makes the balance even. Okay. Now, the mole ratio that we're interested in is HCl to the sodium hydroxide. So, the mole ratio is 1 HCl to 1 NaOH. I'm going to put that as a fraction. You need equal molar amounts, right? It's actually one atom, or one molecule to one molecule. It's an ion compound. It's not really a molecule, but you get the idea. Well, 1 mole of HCl to 1 mole of NaOH. What if the concentrations are different? What if I have, it makes it easy if we have, and I have right here, a 1 molar solution, 1 mole per liter of HCl, and I have 1 mole per liter of sodium hydroxide. So I think you know to get 1 to 1, I just take 50 mils of this, 50 mils of that, and it's going to be equal, right? Bam, done. That's easy. What about if 1.23 or unknown? How do you figure out how much volume adds to that? Well, this is where, and this is a reminder, you're going to use Balance of the base, concentration of the acid, volume of the acid is equal to balance of the acid, concentration of the base, volume of the base. We've been using that equation. Use the titration equation. We're going to be doing a titration lab. Okay. Now, phenol phase is either pink or it's clear. Clear in color. Clear in pink. We'll use phenolphthalein as a clue. What do you remember? And this was at the very start where we did something with how does acid, how does base react to phenolphthalein. You remember what it does? And if not, look back to that thing and tell me what it does. So we're going to use this as an indicator. This is why, to know when we're close to the neutral pH. So I'll just write it down. No. And then as a reminder on here, acid is clear and colorless. I'll just put colorless. Base is clear, but pink. I should have put acidic. Okay. We're going to observe this. Right. So the minute it switches with one drop, it'll go from colorless to pink. You know that it just switched from being acid to base. Does that make sense? That is around where it's neutral. Tells you when to stop. It's the indicator to tell you when it's going to change. And if you remember that graph that I showed you, that pH starts low and starts with an acid and shoots through it in one drop. Okay. This range of pH change. That's what we're looking for. And the whole idea is, now you don't have to draw this. When I put HCl and sodium hydroxide into water, they separate into their ions. We call it ionizing of acids, and with other ionic compounds we call it dissociation. But they're all, they mix up, right? And they form H2O and HCl. Right now, in the left beaker, they're just strictly acid. I'm going to use a burette, which you've seen before, and we'll take a look at it again, which is basically like a graduated cylinder with a little tappet to allow it to just drip, 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 right? And when I add it in, so I'm dropping it in, and then there's some sodium hydroxide. The really important thing is that the H's and the OH come together. Okay, right now I've reduced the acidity of the left beaker. Added some sodium hydroxide. I'll add some more. It'll still be clear and colorless. So add some more on the sodiums, hydroxides. Okay, another neutralization there, right? We're not quite there yet. One more drop. And I'm just, you know. Okay, we finally got it. You see that all of the waters are formed here. Right? This would be neutral. This is the idea. You drop, drop, drop until you have all the hydronium ions. I'm not going to show it as H0+. So I'm just saying the H pluses that make hydronium are attached to hydroxides to make water. It neutralizes. So we're drip dropping. That's what's going on. I will demonstrate. I'll pause the video. So we've kind of demonstrated how the apparatus works. Now, the other thing that's new to you is, I'll give you a benzoic acid calcium hydroxide. But what does that 5% mean in the vinegar? And we're going to use a 2%. So I'll give you this reaction. Benzoic acid, C6H5. Then it's organic. So organic acids end with COOH. Yes. Two, calcium hydroxide. Now, here's the weird thing about these. I'll tell you. Organic acids, the acid, the acidic H that leaves is the end, not like HCl or HNO3, etc., where it's the front edge. Organics is the last one. So when that's removed, which it will be, you have this ion, anion. And we're going to put the calcium in front of it, though, okay? So that's the only exception to the rule, because generally you always put cations first, but the H in that case is attached to the end. So here I go. We've got calcium, but I know something about calcium. There's a 2+ charge on the benzoate anion has a -1 charge. So I'm going to say calcium bracket. COO, taking off the H. That's my salt, plus water. Now, I've got to balance this. The way I think of balancing is I've got 2 OH groups, so I know I'm going to make 2 waters. So I'm going to put this in, that's disappearing in. So that's what I think. So I'm going to balance it. I've got 2 waters. I know where those other 2 H's, front H's came from the acid, right? So I need 2 H's from those. That's what I think about. Now, taking care of the single H's, the benzoate, the C6H5COO particle. I notice I've got 2 on the left, and I just so happen to have 2 right here. So this takes care of everything, doesn't it? Take care of the water, then you just double check it. And that's why I recommend writing water as HOH. Do it as H2O. I use this benzoic acid as an example because vinegar happens to be a organic acid as well. Okay? More about that. So it works with the COO end. Okay. Now another question. Molarity of 2% HCl solution. What is a 2% solution? What does that mean? Well, here's what we're going to write. 2% means that I don't care if it's HCl or vinegar. It means 2.0. Now, it's 2 mils out of 100 mils. That's out of 100 is a percent, right? But it just so happens that the acids we use are mainly water-based. You know what the density of water is? How many grams of water make up a mil? 1 to 1. So if you have 100 grams of water, you have 100 mils of water. More or less. It's perfectly fine for it to be. Anyways. So we're going to say that this is actually 2 grams of the HCl solution. So 100 mils of water, what my point is that 100 mils of water is actually 100 grams. It's actually a weight percent. I kind of said it backwards. Anyway, but it is 2 grams of HCl to 2 grams of, to 100 grams of water. But 100 grams of water is 100 mils, and that's what we actually get. So that's what that means. But we also know that we probably want to operate liters. And just by looking at it, I know that 1,000, right? I know that that's actually decimal 100. So when I say a 2% solution, I'm meaning grams per 100 mils. And I know that that's actually 0.100 liters. So to get moles, you've got to get moles. 2 grams of HCl. If I add up the H and the Cl, 1 mole, so 4 moles at the top of 1 gram, that is what? That added up. Now let's see. 1.01 Cl, 35.45, 35.46. Or did I say 30 plus 1.0? 36, of course. When I calculate that, 2 times 1 divided by 36, 0.05 CL. That's the moles. And I wrote down grams. Stupid, thank you. Thank you. So now my concentration. So that 2% solution is really something that we use in chemistry. Moles divided by the 0.1. We were assuming that the top 100 mils was 3 significant. You can actually measure more. And the math there is pretty easy. 0.055 divided by 0.1 is 0. Right again. 0.55. Okay, well, trust me. Okay. So, here's what you want to do on your last page, and then we'll get back to your others. Right there is what we're going to do this. Find the concentration of acetic acid in 5% vinegar. But we can have a hypothesis that's actually, we should know what, if it's truly 5%, we know what our moles per liter should be. Since the solution is 5%, the molar concentration of, you're going to fill that in, you're going to do your work right underneath this. You're going to convert 5 grams per 100 mils, and this is the formula of acetic acid. That's true, right? It's an organic acid. You can add up your season ranges. You can convert that and actually figure out what it should be. So you have if it's truly 5%. Now that's 5.00%. You're assuming. You're going to go with that kind of accuracy. It could be anywhere from 4.5 to 5.4. Or you might find out that this is false advertising and it's higher or lower, right? That's what we're doing. We're going to save that though. I'm not going to do it with you. You're going to do it for me, for Mark. Okay?